He kōna e purangi tēnei nā te reo irirangi o Aotearoa.
If I said space rockets, what would you think of? This, of course, a rocket launch. The massive, explosive chemical propulsion needed to launch a rocket through Earth's atmosphere and into space. But once in space, how do you move your satellite, your ship, your capsule, your whatever? Well, one of the answers for that is to use an electromagnet-powered plasma rocket. And if a team of New Zealand scientists and engineers have their way, these might soon feature a particularly powerful and efficient kind of electromagnet. Kia ora, nau mai hara mai ki te ao hurihanga. Hello and welcome to Our Changing World. Ko Concannon tēnei. And today we're talking about plasma rockets in space, which sounds totally exciting. Like the blue plasma, and yes, it is blue, would be firing out the back loudly, accelerating things forward aggressively. But that's not quite it.
Many of these thrusters, the amount of power that they put out, the amount of thrust that they provide, is about the weight of a piece of paper on your hand. So not much, but because there's no air to push against and they are away from the gravity field of the Earth, that thrust can be used over weeks or months or years to build up great velocity.
This is Bettina Pavry, a senior principal engineer at the Pi Hau Robinson Research Institute in Lower Hutt in Wellington. She's got a car analogy for the difference between the rockets.
You might have, say, two kinds of cars, a muscle car if you want to go really fast in a very short period of time, or if you want an efficient car that will use the minimum amount of fuel to get you to your destination, you have a different set of criteria there for what's important. So we have these two different kinds of rockets, and we're looking at improving the efficiency of the second one.
And in your analogy, the second car is also just on this super slick, non-friction road where if you give it a little push, it's just going to keep sliding.
It's going to keep going. And so even though the amount of pushing is small, because there's no friction, there's constant acceleration, and you can build up great speeds over a short period of time.
Now, this is not Bettina's first space rodeo.
I started work at NASA's Jet Propulsion Laboratory back in 1985. So JPL's area of expertise is the robotic exploration of space, so rovers and orbiters and things like that. And so my background, I have actually a crossover between engineering, physics, and planetary geology. So that ended up being a great background for working between scientists and engineers and understanding how to design machines that would solve science problems.
We're in Bettina's office, and across from her desk is a series of picture frames, each with a poster of a different NASA launch, each representing a mission that Bettina has worked on.
One of the first missions that I worked on that went to space was actually a Earth-orbiting satellite, had an instrument on it called AIRS that was making measurements of the Earth's atmosphere. Then worked on a mission called Mars Reconnaissance Orbiter, which, as the name implies, was a orbiter that was making a lot of measurements of the Mars surface and atmosphere from orbit around the planet. Then worked on the Dawn mission.
The Dawn spacecraft that launched in 2007 is an example of a mission that used these kinds of low-thrust but super fuel-efficient rockets. It travelled to the dwarf planet Ceres and a protoplanet called Vesta, located in the asteroid belt beyond Mars. Here's a clip from a 2016 NASA video with the Dawn mission chief engineer Mark Raymond.
It would take Dawn 4 days to accelerate from 0 to 60 miles per hour. But instead of thrusting for 4 days, if we thrust for a week or a month or a year, or as Dawn now has for 5.5 years, we can achieve fantastically high velocity. And so this is what I like to call acceleration with patience.
But back to Bettina's previous missions.
Then worked on the Mars Science Laboratory, the Curiosity rover mission. So that's kind of a whirlwind tour of my career, and now very much enjoying my new role here at Pi Hau Robinson, working on this technology demonstration mission of the plasma rocket and its superconducting magnet.
Yes, the plasma rocket and its superconducting magnet. There's so much cool terminology going on here. But wait, there's more.
We're using an old new type of plasma rocket, so it's called a magnetoplasma-dynamic plasma rocket, MPD.
It's a cool name.
Yeah, it's pretty cool. And we're putting a powerful HTS magnet around it.
This is Dr. Ben Mallet, a senior scientist at the Robinson Research Institute, which, not coincidentally, is known internationally for superconducting magnet science and engineering. Now, a superconductor is something that conducts electrical current with no resistance once it gets below a certain temperature. Initial superconductive materials required extremely, and I mean extremely, cold temperatures. And that's why Ben has said HTS magnet, because it stands for
High temperature superconductor. So it's a superconductor has zero resistance to electricity. It means you can put a lot of current through these. They don't heat up. You can make really powerful magnets.
And just to clarify, because when scientists say high temperature superconductor, they're talking about a different kind of high temperature than the normal person would be talking about.
Yeah. It's all relative, isn't it? It's, about minus 200 degrees Celsius. We're using what we call a cryocooler, which is kind of like a fridge, and you give it power and it can cool down your magnet to those sorts of temperatures.
So, I mean, that sounds awkward that you would have to have a magnet that has its own, like, self-cooling cryo chamber to go with it. What is the advantage that a high-temperature superconducting magnet brings to the table?
So this particular type of plasma rocket does really well at high powers. So that's if you want to go very far in space, if you want to transport cargo to the moon and back, or if you want to go even further to distant planets, that's where you want this particular type of rocket. So a plasma is a charged gas. It's got the positive and the negative charges in there, and that means you can use electric fields and magnetic fields to accelerate it, and that's how you get these really spit out your exhaust really quickly. So that's what where the superconducting magnet comes in. It generates these really powerful magnetic fields to help accelerate your plasma to spit it out the back of your rocket really, really quickly.
In space, you want to make things as light and as efficient as possible, and the superconducting magnet might help improve both of these. So we've got the high-temperature superconducting electromagnet that will power the thrusters on the rocket, and it has its little cryogenic cooling chamber. But it also needs one other thing, the electro part, the current, which is what Ben is focused on.
I'm making something called a flux pump, which energizes the magnet, which puts current into the magnet to make this powerful magnetic field. Flux pumps are great because they can put a lot of current in and they don't take a lot of power to do that. And that's really important in space. Any way you can reduce how many watts you need, how many watts of power, is good.
To be clear, it's not just Bettina and Ben working on this. There's a team of people within the Robinson Research Institute, and they're also partnered with the University of Auckland and the University of Canterbury. And they need a team, because there's a lot to make and build, and then test, before this new plasma rocket design can be used. Part of Bettina's role is to think about all those things you need to consider when you're building something to operate in space.
My background gives me some insight into what can go wrong in space and how we make sure that the things that we build on the ground in the lab are actually suitable to survive the environment of space and the journey there. So, for example, if you put something on a rocket to go into space, it will experience severe shaking. So we need to qualify anything that goes into space to make sure it'll survive that environment without breaking. We need to make sure that it will survive the radiation environment of space, and all of the radio signals, for example, between the rocket and the ground and so forth won't interfere with it, because the environment of space is very unforgiving, and once we send something there, we can't fix it, right? It has to work the first time. And then there are things that folks might think about, for example, there's no air, and air is a great way to get rid of heat. So it's very easy for things to get too hot or too cold without air around them. So we need to, for example, place our experiment into a big chamber, pump out all the air, and make sure it's going to not overheat in that environment. So that's an example of the kind of problem we need to solve when sending things into space.
It's a lot to think about. So they've broken it down into 2 smaller projects that they're doing in parallel. The first they've called Concannon, because the bright blue wattle of the North Island Concannon matches with the blue plasma that comes out of the rocket thruster. This is where they're testing the performance of the thruster and superconducting magnet combo in a chamber that simulates the vacuum of space. I mean, there's basically no point in doing this if the fancy magnet isn't able to make the rocket better. The second part is called Heki, or egg, and this is where they've carefully designed a container, around 30 centimeters squared, that has all the parts that the superconducting magnet needs to work. So the magnet itself, the cryocooler, the flux pump, and the computer and electronics, encased in an aluminium cover. And that is going to be sent to space.
So we're hoping to launch in early 2025, which means that in late 2024 would be when we'd be doing all this testing. So here we are in 2023, so we're in the middle of designing, building, testing, finding out where we have problems, redesigning, and responding to those challenges. So when you design something new from scratch, you find out how much you don't know. And so that's why it's really important to do this iterative process where you design, build, test, fix your problems, and then test again. So that's the part we're in right now. And so by the end of next year, we are planning to have the whole thing built up, ready to go into this environmental testing, and then ship it to Houston for its start of its journey to the space station. We're working with a company in Houston that has essentially slots on the space station where they can put experiments. So we coordinate with them, and they tell us how big it can be to fit in the space, how heavy it can be, what kind of environments it needs to survive. And then they arrange the journey there for us. And when we get to the space station, the astronauts will install it in its little slot. And then we operate for about 15 weeks. And then they send us back down so we can make sure to take a look at our experiment and see whether it's been changed by the exposure to the environment of space. So part of our goal here is to show that this is a viable technology, it operates successfully in space, and that it won't degrade in that environment. That's another important part of the story.
And one thing they're keeping a particular eye on is radiation, and how the fancy new magnet might interact with the radiation in space, because it might also have the potential to work as a radiation shield.
Along with that experiment, we're going to be flying some radiation detectors to determine how the presence of the magnetic field changes the radiation flux that is received by the Heki electronics. And that's really important because for both electronics and people in space, radiation is a huge problem. It's not only unhealthy for people, but can also really impact the functionality of electronics. So anything we can do to mitigate that effect is really important. So that's part of the science demonstration that we'll be doing.
The team has been working on this project for 3 years, but off the back of a lot of institutional knowledge. Ben tells me where he's at now with the flux pump design.
We've been working right from sort of prototype, bits and bobs in the lab, through to mechanical, electrical design, testing and liquid nitrogen, through to quite a sort of polished sort of product now, and that we're integrating it now with the rest of the system and to test its performance. The Institute has been doing flux pumps for quite a has quite a reputation for flux pumps, and we make various types of them. This is a particular type which we're really looking to demonstrate in a really exciting environment, and I think it'll really prove to the international community how useful these flux pumps can be.
We head off down the hall to have a look at the lab space where they design and build and test. On the way, we pass by an empty, spotless room.
So this is the clean room where we'll actually be building the rockets. We'll be building the experiment once we're ready to send it to the space station. Right now, we're building everything in the lab.
And it's a clean room in what way?
So it means that the air inside is it's filtered a lot such that it doesn't have any particles in it, and the people inside wear special clothing to keep grease and dust and so forth off of our experiments so that when it gets into space, we haven't contaminated it with anything and it will function as expected. So it's part of making sure that what we send to the space station will actually work effectively.
Down the hall, through a few more doors, we come to the massive lab space where there's a lot of different things going on. At the end of the room is a giant, bright metal capsule, key to the testing of the Concannon side of things.
So this is where we try and simulate the environment of space so that we can assess how our plasma rocket's going to work in a relevant environment. This particular one's called a gigantic and extremely radical atmosphere-lacking device for interesting and novel experimentation, also called GERALDINE.
Geraldine, very shiny. Geraldine is very shiny. And so what happens inside Geraldine?
This is the main test facility for our plasma rocket.
And so all of the air is sucked out of Geraldine?
All of the air is sucked out. We use various types of pumps to do that. We put various bits of instrumentation inside, like a way to measure how much thrust is being produced, how much force this plasma rocket is generating. It's quite a tricky problem actually because it's got to be very sensitive. We also have various cameras and whatnot to inspect the glowing blue plasma that comes out of the rocket.
Was Geraldine made here for this purpose?
Yeah, it was made specifically for plasma rocket testing.
Yeah, someone has got quite creative with the names in this lab. Because alongside the gigantic and extremely radical atmosphere-lacking device for interesting and novel experimentation is the big empty receptacle for thruster impulse experiments, which, yes, is known as BERTI, and is being used to help with that tricky problem of how to sensitively measure the amount of thrust being produced.
So at the moment, BERTI is being used for developing and validating the performance of our thrust balance, so the device which is going to measure actually how much thrust this plasma rocket produces.
It's a big, high-roofed area with the vacuum pumps making a lot of noise. But in the centre of the room, on either side, are two large lab benches, and there are people busily working away, concentrating hard.
So this is Xiong. He's another one of the scientists here in the team, and right now looks like he's making parts which go on the superconducting magnet. So he's got a piece of superconducting tape there, and a big soldering iron in his hand, and he's going to solder the pieces of superconductor together. There's obviously science in it, but there's also a bit of art in just how you do the soldering, so you have a very low resistance join between your superconductor. And that's something that we've developed really, really well as part of this project.
Yeah, it looks like a very delicate operation between the soldering iron and there's a pair of tweezers and almost looks like painting.
Yeah, I find it quite cathartic actually to
assemble an old superconductor.
Yeah, and you get your solder to flow over the superconductor just right. It's quite satisfying, really.
The magnet itself is a cylinder shape, and on the bench behind Dr. Xiong Huang, who's carefully soldering, is a 3D printed version of what the assembled magnet looks like.
So this is a little mock-up of the magnet that will be sent to the space station, so you can get a sense of the scale and size. This particular one fits in the palm of my hand.
This superconductor is made up of a series of these coils kind of
all
stuck
joined
together.
Yeah, we've got 4 of these so-called double pancake coils. There's a lot of food analogies actually. This is called a double pancake superconducting coil. Bettina thinks the assembled magnet looks like a
steampunk bagel. I call it the steampunk bagel. It's about the right size, kind of a thick, big bagel.
And we join several of these coils together using the soldering that you just saw Xiong do, and that's to make a more powerful magnetic field. And the flux pump then fits really snugly on the magnet to put current into the magnet, and it will generate half a Tesla.
The Tesla is a unit of magnetic flux density. named after the Serbian-American inventor and engineer Nikola Tesla, who's best known for his contributions to the design of the AC electricity supply system. To give you a kind of a reference point, a fridge magnet, securing your to-do list, is about 0.001 Tesla, and an average MRI magnet, used for medical imaging, is about 1.5 Tesla, though stronger ones now exist. But as Ben explains, they've got more things to think about than just the strength of the magnetic field. Because space.
We're limited by how much stray field the space station itself will receive. So we've had to put a lot of design work into reducing the stray field so that we don't interrupt with the rest of the space station, and that limits our field to a bit.
What do you mean by stray field?
So if you imagine the lines coming out of a bar magnet, like the classic picture you see in these books, those lines are magnetic field lines, and they're stray because they come outside of your magnet. And it's exactly the same with these electromagnets. So they have these lines of field coming out, and the strength of that field needs to be below a certain threshold for safety reasons at a certain distance on the space station.
There are other people wandering in and out and working away at other benches. I asked Bettina, just how big is the team?
15 to 20 people are contributing directly, but then we're supported by a much larger group of people that make this all possible. You have people designing and building the electronics and the cables and machining the parts and all of the support structure that we exist within. So everybody, have a large group of people who are contributing directly to it in addition to the scientists and engineers.
Some of the partner institutes will help them with aspects of the testing, such as shaking the hell out of their prototypes to see if they will survive the journey into space, and testing to make sure that what they've built doesn't make radio waves or electrical signals that interfere with other things on the space station. This is the Robinson Research Institute's first foray into space, and so much of this is about tech de-risking, making sure that what they design will work correctly in space to do its job. The Concannon thruster testing and all the work in this lab is building towards that deadline of the launch to the International Space Station. There, the HECI, with the superconducting magnet, flux pump, electronics and radiation detector, will be placed outside the space station for testing. I asked Dr. Ben Mallet, what's the dream outcome for that test?
Showing that we can operate the superconducting magnet in space, I think, will be a massive milestone. It'll be the first, demonstration of a fully superconducting magnet in space like this, and showing the flux pump technology works as well. I think that'll all be very exciting. We've got various goals and metrics we want to hit. The other really exciting thing, I think, will be the potential to bring this magnet back and then inspect it and put it inside around a plasma rocket.
If they can show it can operate in space, well then that's the validation they need to open commercialization doors. We've been focused mostly here about the plasma rocket thruster application, but there are other uses for high-powered magnets in space, controlling a spacecraft orientation with magnotorquers, which use a strong electromagnet to push against the Earth's magnetic field, or the radiation shielding Bettina Pavry mentioned, or ballistic re-entry shielding. So if successful, it's possible that this technology might be go for launch. Thanks to Bettina Pavry and Dr. Ben Mallet from the Robinson Research Institute. This episode was produced by me, Claire Concannon, with help from Liz Garton and Ellen Rikers. Sound engineering was by William Saunders, and Tim Watkin is executive producer of podcasts and series at RNZ. If you've got feedback for us, you can drop us an email at ourchangingworld@rnz.co.nz or find us on Facebook or X, where we are at RNZ Science. Our webpage is at rnz.co.nz/ourchangingworld. Now, much of the tech that I had a look at in the lab is proprietary, but there is a photo of the beautiful, shiny Geraldine up there if you want to have a look. We'll also include some links to other Our Changing World episodes about superconductors and other research from the Robinson Research Institute. Now, the phrase high-temperature superconducting magnets for applied field magnetoplasma dynamic thrusters sounds like it could come straight from a science fiction novel. If that's your jam, I highly recommend the RNZ podcast Sci-Fi Sci-Fact, where experts from the MacDiarmid Institute take an idea from fiction and see how it stands up to scientific scrutiny. Does the multiverse exist? Could we ever have lightsabers? What about the Dune stillsuit to survive on the open desert of the planet Arrakis? If you've ever pondered these questions, then look for Sci-Fi Sci-Fact on your favourite podcast app or find it under the Podcasts and Series tab on the main RNZ website. Tēnā koe I whakarongo mai. Thanks so much for listening. Ko Concannon aho. Have a great week. Kia pai te wiki.